כן, אני הולך לאיבוד אחר כך. תודה.
באנגלית?
Okay, shalom, kulam. I'm still a little worried that I see less and less people here. But is this every, I don't know if it's just Wednesdays or... So next Monday I'm teaching. And then as I told you I'm going away for 2 weeks, so essentially Ravid will have from next Wednesday, in principle, I return only on the 12th, or 13th or something in December. So we're going to have a long stretch of exercise. I hope that everything will be enough to digest everything that we talked about now. But, I'm sorry?
What did you say? We'll have a long
stretch of recitations, whatever you want to call it. So anyway, maybe we'll skip one to give you a break. But I certainly want to see as many of you on Monday, because I'm going to push some more material just to have something to digest. So we started to talk about a topic that we call parameter estimation, which is actually the first case of what we call learning, and we'll generalize it. So essentially, this is actually already what most people call learning, but this is really the old type of learning. It's classical statistics. And we treat it, at least we started to treat it in the Bayesian framework by essentially thinking about the state of the world as some sort of parameters of a parametric distribution, family of distributions, which can be many different types of distributions, which depend on parameters. And we gave you several examples. I hope that the exercise helped a little bit to clarify it. Bernoulli, Gaussians, Poisson, and so on. Mixtures of such things. It can be very, very complicated parametric families. Actually, I'm going to, when we talk about neural networks, in some cases we think about them as parametric families also, but we'll see that they are actually different in nature from the classical, those simple parametric families. And so we have this Markov chain of the parametric parameters of the world, of the model, which we don't know, which actually generates observations, which we usually call samples, some n-size sample, and we actually think about this sample, at least for the beginning, as IID sample, which means that there are n samples independently drawn from the same distribution with the same parameter theta, which is unknown to us. And then we think about the estimator of the parameter as a number that lives in the same, or set of numbers that live in the same class, the same space as the original parameters, whatever they are, which is some subset of usually Euclidean spaces. So we think about it as continuous variables. And so theta hat is the action formally in the Bayesian framework, but it's actually a map from the samples, which are our observations, back to the parametric families, or parameters of families. Okay, so this is the basic framework of what we call parameter estimation. And I mentioned last time several properties of the parameters of the estimators. As I said, in Hebrew we call them either omed or mesha'arech, which is a bit funny word, but both of them are used in Hebrew. So the properties that one would like to have. So okay, so first of all, in order to complete the Bayesian story, we need to give some sort of cost, which is essentially how much we are going to suffer or pay if if the state of the world was theta, when the parameters were really theta, but our estimators was theta hat. So, and we gave essentially three types of estimators. Two types of costs. One of them was the MSE, actually three. So this cost was essentially just the norm square of the estimator. So remember that theta hat is a function of the sample. I'm going to omit it if I don't have to. So it's actually telling us, okay, for a given, this is the square distance, or the square loss, as we usually call it, square loss, or so it's just the norm, the Euclidean norm, or Euclidean distance square of the distance between our estimated parameters and the true parameters. Of course, the assumption here is that when this is small, we are close to the true parameters. And there's something underneath here which we need to explain. Of course, I also mentioned the L1 norm. So the L1 is the sum of the absolute values over the coordinates. So this is L1. L1. This is turned out to be a very important. This is M here is the dimension of the space. Yeah. So this is just like the Euclidean norm here. It's also the sum of the coordinate squares, but it's more robust in some sense. I mean, it's giving us, as you saw, this gives us the estimator, which was the conditional expectation. So the MSE was the conditional expectation of theta condition on the sample. This is called the conditional expectation. Which is a very natural thing to do in many cases. This gives us something which we call the median, or the generalized median, and this is in some sense more robust, as I already said. So use it in what we call robust statistics. So we want to not to be too sensitive to the tails of the distribution. And I also mentioned, in some sense, natural extension of the error, the probability of error, course, which is just 1 minus delta theta hat minus theta, where this delta is the Kronecker delta. I'm sorry, it's the Dirac delta, which is an extension, a continuous extension in some sense of the Kronecker delta, but it has to be understood only within an integral. Otherwise, it doesn't make sense. And we saw that so this one actually gave us what we call the maximum a posteriori estimate. So we saw at least three types of costs like this. And the map, so theta map, this is just a reminder, was essentially the arg max of all possible theta. Let's call it theta prime, not to confuse anyone, of the probability of theta prime given the sum. So I don't know theta. I maximize over all the thetas in my class. That's a very important measure. The problem is that, actually with all of them, that they all require, in the Bayesian case at least, a prior over the theta. So all these cases assume that we know the model, which means we know P, a prior over theta, and we know the observations given theta. So this is, so the parametric family is actually characterized by these two things. So all those things require a prior. And that's getting more and more complicated and more difficult to assume when we get to very complex parametric families. So it's usually this assumption of prior is giving us some sort of bias, or in later on we call it some sort of regularization of our estimators. They push it to in some direction. And in the frequencies view, priors are not something we want to consider. So in this case, I reduce the p theta, the map posterior estimator to something which we call the maximum likelihood. And the maximum likelihood was essentially the same thing, but instead of maximizing the posterior probability of the parameter given the data, I maximize the parameter, the likelihood of the data. So it's essentially the same. It looks very similar, but it's a slightly different estimate. And this is not a Bayesian estimate, because I'm not really minimizing a Bayes risk in any sense. Okay? But this is still the most popular estimator, and actually the easiest to implement, because we don't need to assume anything about priors. Okay, so I remove this assumption. And of course, the likelihood of the data, for those who, so when I write this theta prime, or before, last time I wrote theta, and it seemed to confuse some of you. So this is some sort of a dummy variable. I'm maximizing over it, doesn't matter how I denote it. So I'm looking for the argument which actually maximizes the data. And of course, this I can replace by the argmax. It's the same as the argmax of a theta prime of the log likelihood. Okay, which is, and actually it's the same if I divide it by n, it doesn't matter. So for every n, this is just a constant positive factor, so it's not going to change the maximum. Yeah, okay. Of course, when I'm now going to change n, I have to be a little more careful.
Why do you divide by n?
Because the log likelihood is going to be the log of a long product in the IID case, and therefore it's going to accumulate and grow like n, grow linearly with n. So it makes sense to divide it by n to get a number which is of order 1, not of order n. Okay? Actually, you see that this helps us a lot. But it's the same thing, of course, because the maximum of this is the maximum of the log is the same thing. And if I multiply by a constant, this point constant, if I give an n, it's not going to change the position of the maximum. Okay? Of course, it's going to be a little more tricky. So then we said, okay, so what are our desires from a good estimator? So the first thing is what we call consistency. So consistency is an asymptotic property, which essentially tells us in the limit of, sometimes people call it consistent in the limit, but it's actually repeating the same thing twice. It's in the limit of large n. In the limit of large n, which means the limit that n goes to infinity of this theta hat of xn. So this is, theta hat is a random variable. I'll say it more explicitly in a second. So in the limit, we want this to be what? The true theta. Yeah, last time I wrote it like this. It's the same thing. Goes to theta in the limit of n goes to infinity, and we actually call it improbability. So improbability means that probability 1 it's going to approach this limit, but there's maybe a zero measure. Now, remember that theta hat of xn is a random variable. I want to emphasize it, which means it actually has a distribution. So just for simplicity, I draw it in the one-dimensional case, but of course in general it's a multi-dimensional variable. And so if I look actually at the distribution of theta hat xn given theta, so remember what I do is this. I first pick theta, or somebody picked theta for me, nature or whatever, I don't know theta, but theta is fixed. I generate a sample, and then I generate, the sample is a random variable, of course. It's a multidimensional random variable, but it's a random variable. So this is going to be a function of a random variable. Can be, by the way, can be even a stochastic function of this variable, not necessarily a deterministic function. But we know already that in general, in the Bayesian case, stochastic decisions don't help us. So I mean, in general, if we know the model, if we know these distributions, then stochastic decisions don't help us. If we don't know them, we are going to see that it's going to be more tricky. But so in general, I can think about it as a function of the sample, but it's still a random variable. Okay, so it has a distribution. So this is going to have some distribution. I draw it like a Gaussian distribution just because it's easy, and it's eventually going to look like a Gaussian distribution, but it doesn't have to be. I mean, and this distribution. So this is the probability distribution of theta height. Actually, it's the density. I'm thinking about continuous variables, so it's the density, the PDF. Yeah, probability is that density function. You know what it is? Yeah. Okay, so this is just like a Gaussian, and it may be centered. So this may be the true theta, and this may actually look like this. Okay. So there are two properties that I really care about. So first of all, the consistency means, first of all, that so this distribution in general has two numbers. Well, I'm going to show you that you already see it, that at least in the maximum likelihood case, this estimator is going to depend on the probability of the estimator is the probability of a sum of many IID numbers. So you already know that sums like this tend to distribute like normal distributions eventually. This is the central limit theorem. So we're going to use this, of course, again and again. But in general, this is going to have a distribution, and this distribution can have a mean. Let's say, in this case, it's just the center, the mode, also the maximum, but it doesn't have to be. The mean can be away from the maximum of the distribution if it's not a symmetric distribution, for example. So the fact that it's actually the maximum likelihood in this case is also the mean. This is just because I'm talking about symmetric distributions, but this maximum, this could be actually two bumps, and the mean would be actually in a very low place or anywhere. Yeah. So the mean is not always the most likely place. Actually, in many cases, it's not likely at all. I mean, just yes.
What is the x-axis?
So this is theta.
Then why is theta also a number on the x?
Yeah. Okay. Going to make my life difficult. So this is theta prime. Okay, what is all the possible values of theta? With the true theta is this one. Yes, you're right. I mean, I had to be more careful. So so this is all possible thetas, and this is the actual theta I choose my data from. Okay, and but so essentially this has a mean, the conditional expectation in some sense of theta is conditioned on the sample. So. Yeah. So the conditional expectation is this, in this case, and it also may have a variance. It's actually given theta or given xn, which are taken from theta. Okay, so essentially the consistency requirement is the requirement in the limit. This distribution is going to center around the true theta. Okay, that's a very strong requirement in some sense. So it's not only going to shrink in variance, but it's also going to be centered around the true theta. That's the consistency. So whatever is going to happen to it, I mean, those distributions are going to get sharper and sharper, but they're also going to be centered around the theta. And asymptotically, it's going to be on theta. So that's
it doesn't say that it's going to shrink. It just says that the estimator would be...
yeah, that's right. The estimator should be theta. Okay, you're right. It doesn't say that explicitly this. But it is going to shrink in most cases. Now, there are two other properties, two other numbers that you immediately see here. One is this number. we have here's a different color. So this number is what? How did we call it? The bias. That's right. So this is the difference between the expectation and the true data. So how far are they? So this is what we call the bias. The bias, and I'm going to define it as what, and just as it is written here. So the bias, or let's call it B, just to simplify things, of theta hat given theta. Again, I'm expressing here the sample which is inside theta hat. So there's a sample of size n here. Is going to be defined as what? As the expectation of theta hat given xn of theta. I don't know if I can write it in many ways. So xn is taken given theta. And minus what? Minus the true theta. Now this is this minus this. Okay. So so it can be a positive bias or a negative bias. In the real numbers, in general, it's a vector. Yeah. It can be. It's just the difference from the mean, or difference of the mean from the true. Yes. So this is the bias. And then what a good property that we would like to have is what? Unbiased. So we want this. In principle, it's a much stronger condition than consistency. So, and that for any n, this difference is 0. Now, do you still see here when I write it here? Yeah. So 2 is unbiasedness. Unbiasedness, okay. Which means that the bias of theta for any sample size is 0. Okay? So if this is true, then we call it an unbiased estimator. Okay? Now, there is another important property that comes from this picture, which is what? The variance. Yeah. So, estimators with high variance are in some sense noisy. I mean, which means that if I take 2 different samples of the same size, I can get very different values of the estimate. Because high variance means that I have probability here and here and so on. So high variance is high spread in this simple term. So essentially, we would like to have small variance. Okay. So we'll see later on this hour, I hope, and that we can't. There is some sort of trade-off between the bias square and the variance. So, in some sense, I cannot really reduce all of them together. So unbiasedness is very clear, and this was it was a very natural requirement in the early times of statistics. But we'll see today in what we call Cramer-Rao bound that the unbiased, if I insist on being unbiased, I'm going to pay a little price with the variance. So the variance is going to be bounded. It can't be 0 in general, unless n goes to infinity. And this is what we call the bias variance trade-off, or dilemma sometimes it's called. And this is one of those things that machine learning changed significantly. I mean, before machine learning, we used to think that unbiased is a very important property, and we don't want biased estimators. But it turns out that you can pay a lot for being unbiased, and actually what is really important is not the bias itself, but the trade-off between variance and bias. We want to minimize the sum in some sense. I'll come back to that. Okay, so the last part of this class, I'm going to prove this Cramer-Rao bound, which is this trade-off of what is the minimal variance, given some assumption about the bias. And you'll see that the minimum variance estimator is a good property. So we would like to minimize the variance. So there's a third condition, which I write here just as a minimum variance. So of course it's the variance of theta hat given theta and we'll see how and when we can achieve this. Okay. Minimum variance estimator, minimum unbiased estimators, minimum variance unbiased estimators are known as efficient estimators. Yes?
So we have this consistency and there is conditions which are redundant in some cases, right?
So you see that I'm not sure I'm not sure I heard you correctly, but of course unbiasedness is stronger than consistency. So if it's unbiased, it's consistent. Okay? Because it's true for any n. Okay? Now, in the limit, good things happen. I mean, so this is an asymptotic condition. I mean, only in the limit of very large samples. Unfortunately, in reality, we never have infinite samples. We have finite data, and we need to live with finite numbers, and we need to somehow so the fact that it's consistent, actually, it's an asymptotic requirement. It's actually a very weak condition, but it's some sort of a minimally required condition. So the first thing I want to show you is that the maximum likelihood estimate. So here's a little theorem. The maximum likelihood. I hope you're not just ML is maximum likelihood from here on. It's going to be machine learning later on, but that's fine. It's ML is right now maximum likelihood. So maximum likelihood is consistent. But I need to define consistent a little bit more carefully. So let me add a condition here for identifiable families. So what is this? This is a theorem. So identifiable families actually mean that I cannot have two different values of the parameters that will give me the same distribution. So let me define it first. So a family I mean a parametric family of distributions. Family, yeah. Theta. So family is not your usual family. It's just a parametric family of distribution. Is consistent, is identifiable. It's called identifiable if the DKL for any theta 1 and theta 2 in my family, if the DKL between these two distributions is the same, is 0, then that's infinite only if theta 1 is equal to theta 2. So let me just space it a little bit. For any theta 1 and theta 2 in my class, in my family, if the DKL, if this can, so if the two parameters are the same, of course this is true, but they cannot have, so you cannot not have two different parameters that have the same probability distribution. So for example, Gaussians, let's say with just constant, the mean is the parameter, let's say constant variance. It is one-dimensional Gaussian, it's identifiable, of course. Why? Because if I change the mean, I change the distribution. They cannot be the same. So, okay, so it seems like that everything that we said so far was identifiable. But of course, you can see, for example, I can have more parameters than needed. For example, I can have parameters which are linearly dependent somehow. So for example, I can have two ways of writing the same distribution. For example, if I'm talking about a mixture of two Gaussians. So a mixture of two Gaussians, something like this. So this has parameter mu1, sigma 1, mu2, sigma 2, so you know what I mean. Yeah. And let's say that I'm talking about some lambda normal mu1 sigma 1 plus 1 minus lambda normal mu2 sigma 2. So this is, there's at least a trivial symmetry here. I can replace mu1 by mu2 and sigma 1 by mu2, and then lambda and minus lambda. So in these 5 parameters, lambda, mu1, sigma 1, mu2, sigma 2, it's not identifiable, because I can write the same distribution in 2 different ways. Okay? But this is simple. This is just replacing the two variables. But in general, if you think about more and more complex distributions, it's getting less and less identifiable. Actually, in general, let's say when we talk about neural networks or something like this, which have many parameters, it's absolutely not identifiable. Actually, there are infinitely many sets of parameters that give you exactly the same network. So this is this innocent-looking requirement. It seems reasonable. Yes, I want my family to be identifiable. Is actually almost never met for really large models. Yes.
But this is not identifiable only if lambda is on path.
If lambda is what?
Is path.
No, I can switch. I mean, so in principle, this has 5 parameters: lambda, mu1, mu2, sigma 1, sigma 2. Okay, let's just make it simple. This is my theta. Okay. Now, so these two distributions, this one and this one, 1 minus lambda, mu2, mu1, sigma 2, sigma 1, are identical. For any lambda, it's exactly the same distribution. I just switch these two. It's the sum of the two. So and they are not necessarily the same. I mean, mu1, mu2 can be different, and so this is not identifiable. But who cares? Okay, so you're going to see. Now this is a simple symmetry. So it's obvious that if I just with some technical correction addition to this, so up to permutation. But in general, let's say we'll talk about mixtures. For example, we'll talk next week about Gaussian mixtures or about clustering and things like this, which some of you may know from other places. So then it's not identifiable. I can take any permutation. Here it's just a switch of 2, but I can have any permutation of my clusters, and it will be the same model. So in general, so people can still restrict themselves to up to permutation and things like this. But in general, when you start to talk about really complex models, the identifiability is going to be impossible. Actually, we're going to have infinite continuous manifolds which are all the same distribution. But at this point, I want to assume it, as done in classical statistics book. And so I claim that if I'm identifiable, then the maximum likelihood estimate is consistent. Why are you laughing? I mean, okay, never mind. So how do we prove it? This theorem. Okay, so in principle, it's very simple. You just write this theta ml for a given sample explicitly. So what is it? It's written here underneath. So this is theta ml. I don't want to copy it. So again, but what I do want to see is to take the limit of theta ml, and I want to prove that this is consistent. Okay, how do we do this? So this is the reason I'm actually showing this proof, which is of course in Amir's note also, is because it has some important lesson inside it. I mean, proofs are interesting. Proofs are valuable to see when there is something to learn from the proof. It's not just a technical proof. Sometimes the proof itself is much more interesting than the theorem. I mean, sometimes you see through the proof a lot of things that you don't see from the theorem. So in this case, it actually tells us something. Question? No. Ask question because I'm going to run away now. Okay, so theta ml is this, which is what is the limit n goes to infinity of the the argmax over theta prime of, okay, so I already wrote it, this is the same as this, so I'll put it here. So it's 1 over n log of p xn given theta. So theta prime is this dummy variable over which I'm maximizing here. Nothing more than that. And okay, so now I want to do something which is a bit ugly or tricky. I want to put the limit inside the maximum. When can I do this? Is this always true? Have any sensitivity to this type of things? So I want to replace the maximum with the limit. So in order to do this, first of all, you have to. I want all of you to be aware of the fact that this is not always possible. It's not always true. But let's say, as long as I'm talking about finite n, that's not a problem. Okay. As long as I'm talking about fixed n, I can replace, if it was, for every finite n, I can first maximize. So essentially what I do here is for every n, I find the maximum, and then I look to take the limit. That's what's written here. You first find the maximum for a given n, and then look at this series of maxima and take the limit. Okay? Now, think about it for a second. When can this be a problem? But let's say that I can do this. Okay? So if I can do this, so this should be the argmax. And I put a big question mark here. This should be the argmax over theta prime of the limit. N goes to infinity of this 1 over n log. And I already assume that this is IID, so I can write the log of the likelihood as well as the sum. Okay, so this is the sum of over my sample of the log of p xi given theta. Okay? So here all I did is assuming IID. Okay? But this should look familiar. So, okay. But this limit, if I first take the limit, what is this limit? Okay, so we saw it already. So what is this limit? To erase the. I want to think a little bit about it. Okay, just before I. It looks very, again, innocent. Okay, so first take the maximum and then the limit, or you take first the limit and then the maximum. What should be the problem here? So think about cases when this is true, but of course I'll answer it. I just want you to spend a little time thinking about it until after the break. Okay, so should do something during the break. That's not. So anyway, but what is this? The limit. So remember, this is, you already saw it when we talked about sequential decisions, or the DKL the first time I introduced it. So this is an average, an empirical average of log likelihoods. So this empirical average, it's empirical over IID. So each one of these numbers is an IID number. So the empirical average converges to what? In the limit? To the expectation, yeah. So this, I'll just continue here. So this is just the argmax over this theta prime. And instead of this limit of 1 over n, I can write an expectation. Sum over all the x's. So everything that is in the brackets here, the square brackets, is essentially the expectation of what? Of p of x given theta This is coming from, because x came from, remember, xi, each one of them was distributed according to my distribution, px given theta. So this is an average with respect to the true distribution of the data, as before. That's exactly the point I want you to see. So yeah, this is approaching this. So essentially, why? So what was the assumption here? The assumption here that the number of times that x appears divided by n is essentially px given theta. So in this sum, the sample is very large. I'll see a certain x exactly this number of times, and then when I divide it by n, it's going to approach the true probability distribution. So this is approaching in the limit this number. This is the asymptotic condition here. So this is a very important assumption. Sometimes we call it ergodic assumption to make it very fancy. Essentially, it's the assumption that my sample, if it's very, very long, is going to sample all the points exactly in the right probability. So the number of times I'll see x, yeah, okay, maybe this, how do you call it, hashtag? Yeah. This hashtag x is essentially the number of times that n appears in my sample. Okay. This is the number of times as x appears. Now, if x is discrete, then it's easy. Okay. Let's say it's a die with 6 faces. So I'm counting how many times 1 appears, how many times 2 appears, and so on. And these numbers are going to converge to the true probabilities. If x is continuous, I have to be a little more careful with what I mean by that, because it's actually never going to repeat. So I have to bin it somehow. I have to discretize my variable. This is a trick that we do all the time with continuous variables. We actually think about them in boxes, and then take the boxes to be very, very small. If you haven't seen it until now, you'll not get it now, but this is essentially the trick. So this is in the discrete x, this is simple. In the continuous x, it's going through some sort of discretization and binning. Okay, but that's a very standard argument. It's a very important argument. Sometimes we actually call this ergodic, in a sense, ergodic assumption. But if you don't remember this, I'm not going to ask in the next exam. So, okay, so what's going on here? So if this is the case, this is essentially the same as the argmax of, okay, so there's p with one theta here, and p with another theta here. Okay? One is theta, one is the true theta, and the other one is my theta prime over which I'm going to maximize. Yeah. So what does it remind you? Yeah. So this is going to be the argmax of minus the DKL of px theta to px theta prime. What did I do here?
But you didn't divide.
Yeah, that's right. So I have to add something. Plus, so it depends where I put the minus here. This is the minus. So I add and divide the sum of px given theta log px given theta. Okay? So let's check the signs again. So this is going to be in the numerator. It's minus. Never mind. Okay? So, but this what is independent of theta prime. So when I take the maximum or take the derivative, that's a shift for all the theta primes. So this is actually what we later call the entropy of P, but it's independent. It's independent of theta prime. So because it's independent of theta prime, I really don't care when I do maximization. It's just shifting my old function by a constant, which depends on theta, but theta is fixed here. So essentially this is the same as the argmin of the KL between px theta and px theta prime. What I mean, because I changed the sign. Okay? Yes?
This should be plus, right?
The first one?
No. I mean,
this?
Minus, yeah.
Maybe. This is one of the things that I always, if I can be confused, I confuse with the sign. This is, always check my sign. But after that, usually I'm okay otherwise. Yeah. Okay. It's not important, because it's just a constant shift. So it's minus the entropy. We don't know what is entropy, but this is entropy. So essentially, we actually find something very nice. So we see that theta ml is precisely the minimum, the one which minimizes the KL that minimizes over theta prime, so all theta prime here, of the KL between my true family. So obviously this is going to be 0. The minimum is 0. If and only if theta prime equals theta, if my family is identifiable. So this is going to be actually theta if the family is identifiable.
Why only if it's identifiable?
Here I use it.
No, but what happens if it's identifiable?
See, my definition of identifiability is that the DKL between two theta is 0 if and only if there's the same parameter. So here's where I'm using it, only here. Otherwise, so this is where identifiability is used. So this is equal to theta. But if it's not equal to theta, then the minimum will give me an equivalent theta. Something else which gives the same distribution, the closest possible to. Okay, but notice that we actually showed. I'm time is out, and I really promised to be on time. Yeah, so the minimum is going to be 0, because the minimum over all theta prime between these two things, which are in the same family, is 0, of course. No, but this is 0. This 0 is actually giving me the true theta only if it's identifiable. Otherwise, I can get a different theta, but it's the same distribution. Okay, so that's where I use identifiability. But that's not a very important use, actually, because in practice I really don't care. If this is 0, then I found the right distribution, and that's all I care about. I don't really care about the value of the parameter. Okay? Remember that. Okay, let's take a break and think about this question, if you can. Okay.
Deze function as
אז לא חייב להיות על בית. זה יכול להתכווץ רק בסוף, סוגרות, זה יכול לזוז לסוף. אין הבעיה שיכול ללכת לאפס בסוף. לא, זה לא חייב להתכווץ. נניח שמעת לדעת לנושא את הנקודה הזאת. לא, אני אומר, לא, אבל בעצם מה שהקומה שאני דורש זה שהבעיה תלך לאפס. לא חייב לדעת. נניח שהמקסימום לייקיות הוא באמת תמיד מוצאים את המקסימום שלנו. זה בעצם מקסימום פוסטריורי אומר שאתה לא חושב. אמרתי שפה. המקסימום פה זה בדיוק התטא מק. ובעצם מה שאני אומר שהתטא מק, הבעיה זה ההפרש אז אני אחפש המאפ יהיה unbiased רק עם ה... אז זאת ההתפלגות הזאת.
זה ההתפלגות של המאפ?
זאת ההתפלגות של ה-estimate.
נגיד של המאפ?
המאפ הוא תמיד המאפ המשפטי.
אני חושבת שכהתפלגות של המאפ. אני חושבת שכהתפלגות של המאפ.
לא, זאת ההתפלגות של הפרמטר. את צודקת. זה לאיך של estimate. מאפ יש לו פילוג. נכון. עכשיו הפילוג הזה...
אז כל נקודה פה היא מאפ אחר. המאפ הוא לא מאפ.
זה צריך ללכת לדלת פאנקשן. זה מה שקורה בגבול. אחרת זה לא יהיה שחק, זה יהיה שחק שחולקת ללכת בגבול למשהו אחד בלי לתת האמיתי. אבל הבייס עדיין יכול להיות רק ללכת אסימפטוטי. גם הבייס וגם הבייס יכול להיות אסימפטוטי.
אני מבינה אבל בדיוק נכון, אחד הוא סנסטיבי, אני יכולה להשתמש, ויכול להיות אחד נכון, אבל
זה לא יכול להיות unbiased. אם הוא unbiased, לא, את צודקת. אני חושב צודקת, יש כאן משהו. זה משהו רגיש שאני לא אמרתי טוב. זה יכול להיות, אם הבייס לא הולך לאפס, זה יכול להיות unbiased ולא חשוב. צודק. נגיד זה בכל מה.
יש שאלה.
כן.
Then universe, max, max and limit.
Yes.
Is it related between the series is like growing and mathematics?
Yes. So it's related. It's related. The question is really my class is compact.
The class of
The class of parameters, the parametric class of compact. So let's say where is it not true? So okay, I'm going to show it in a second to everyone. But let's say the 0-1 interval, and let's define the set of function fn of x, which is 1 when x is between 0 and 1 over n, and 0 otherwise. Okay, so this is like this, which are going to get shrink. Now I'm talking about the inside the interval, okay? Only inside the interval. So my theta is open, it's not compact. And now if my theta is an open set, then the maximum for every n is 1. But if I first take the limit, the maximum is going to be 0. Because the limit of the maximum, the limit is going to push me to this delta function here, but this outside my scope. So in the limit, the maximum is 0.
I've read
So you have to be essentially so these are some of the technical conditions that they have to require. That, for example, if I'm in compact spaces, the 0 point is in my space, I'm usually okay. So if I include delta functions, let's say, or things like this, if I compactify my parametric family, so for example, Gaussian includes all the limits of Gaussian, so which means delta functions sometimes. So if the limits of Gaussian, so if this theta is the compact space, then I'm usually okay with it. But if it's not compact, like the 0-1 interval, then the limit is going to push the maximum outside of my domain. And this can be a problem.
Isn't it what happened to the Gibbs phenomenon in Fourier analysis?
Yeah, it's a little more complicated with the Gibbs phenomena. Gibbs phenomena, yeah, that's right. So the Gibbs phenomena, you can have this non-uniform convergence, but convergence is the mean. It's a similar thing. I mean, in the sense that you have the limit, you can get something which does not converge to a function because you have this infinite oscillation in the limit. So again, up to sets of measure 0 or things like this are okay, but in this limit, in the discontinuities of the function, the Gibbs is not going to converge to anything. It's actually even worse than that because it's even in the norm, in the maximum norm, you have very large deviations. So the Gibbs is even more complicated. But all I want to do is to notice this can happen. But essentially you can have, if you first take the limit, you push it outside, and then the maximum is 0 in the limit. But that's, not only from a mathematician.
And I had a question about ergodicity. So the condition of the resistance is true only if the likelihood is constant with time. Well, is it a matter of time or is
Yeah,
it more
so that you can think about the large n as adding more and more time, which means that every I think increasing my sample is also increasing time. In that case, I'm having this average. I really want that my sample really cover my space in something, which is really everywhere in right density. So it's a finite sample, but I want it to fall in every subset of theta which has of x which has certain probability. I'm going to reach eventually. So there are no holes in my cover. So I'm essentially I cover correctly, I measure correctly all my sets, all my squares.
Okay.
And this is called an ergodic assumption. So it's just like taking in time. Usually we say it in time. Is correct to say when we talk about trajectories, and we say that they are ergodic if they are eventually have a probability of hitting every sphere of every size in exactly the right time, right number of times. So this is not a trivial assumption at all. I mean, it can take forever. But let's say that you have this square, and now and you divide it into small squares like this, and you want your sample to eventually cover all the little squares in exactly the right measure, even when the squares become very, very small. So this is tricky. Mathematically, you have to be careful with this definition. When you want first to take a partition of the space, then take a sample and ask it to actually in the large n limit, you really find points in every one of those little squares in exactly the right measure, and then you take a partition to be very fine and extremely. So it's some sort of two limits. I mean. Time goes to infinity, and the size of the partition goes to 0. This is why it's tricky, and I don't want to. So it's a competition between two limits, but that's how. But in our case, all I'm saying, okay, we have finite space. Think about finite spaces, and I'm just drawing points here, and I want essentially the number of points that fall within each region to be proportional to the measure of precision. That's the manipulation. So this happens. Essentially, the number of times I see x over the total number of times is going to be proportional to the probability of this region.
Easy rules to determine whether an environment is well. We can assume that this make this ergodic assumption, or is it always? I mean, are there because in some time, for example, there is a story about when you know the sports where you have there's the ball and billiard. There's a story about that if the table is rectangular or square, the system is the position is ergodic, and it's
much more difficult question. So then essentially any trajectory which is sufficiently I may have some very special trajectory. The billiard, you have this equal deflection angle. So maybe I can have things like this, even in a rectangle. If I am curvedly, so essentially this angle has to be always the same. If I start from the center here, I can have a circular periodicity. But if you start at any other angle, you're going to cover it. So usually when we talk about the ergodicity of the billiard table, it's precisely that. So the set of angles or points with which I can exactly do a periodic angle here is 0. Essentially any other trajectory will do things like this, I don't know, and jump here and here, okay, and eventually cover the space. And this is then what we call the ergodicity of the trajectory in a billiard table. This is actually not an easy problem at all to prove. It was in mathematician here.
Yes, it was just my question. It's not trivial to know sometimes whether.
This is not a trivial condition.
Okay.
But in general, under general conditions, there are no special symmetries and things like this, and you are going to have ergodic trajectories. But that's a very hard question. Proving that something is ergodic can be technically very involved. We assume it, but it's not easy to prove. But if there are no symmetries and there's some noise in your trajectories, they're usually going to cover everything eventually. But in mechanics, proving that a certain trajectory, a certain dynamical system is ergodic can be a big headache. So it's an assumption we're making because it makes life easier statistically. And we know that a single trajectory, a single sample is going to eventually sample almost once in the right probability. That's the assumption. So the assumption here is that my long sample, this infinitely long sample, is going to reach every x in the right probability. But when you talk about dynamical systems, there's another thing. I mean, there's time, there's the dynamics of the system, so the x's are not independent. Because each x is generated in the next x, and so it's actually Markovian related, and then it's a much harder assumption. For a Markov chain, a Markov process to be ergodic, well, it's technical condition about condition probabilities that you can easily satisfy, but it's much. Here I'm talking about IID, so there's no. In dynamical systems, there's Markovian assumption. Each x is generating the next x. And then talking about deterministic dynamical systems and say that they are ergodic, this is hard. Like your billiard case. Can be done in any cases, and actually the assumption is not so big. Usually what people do is they add a little noise. They take the dynamical systems and add a little noise to it. And with a finite noise, it's going to be ergodic much easier. But with noise, with noise, for example, this very special trajectory is going to be destroyed because I'm not going to be exactly at the right angle. So usually the mathematical trick is add noise, a little noise, and then take the noise to zero. The limit of the noise to zero. And that's how this propagates.
It's more a physicist.
That's right. Yeah, you do it also in mathematics. Actually, this is a mathematician too. I mean, add noise and take. Actually, strictly speaking, you cannot talk about deterministic dynamical systems and say that they are ergodic without this assumption small. But you can take the noise to zero there. In the limit, it's still ergodic.
Okay.
Okay. What's your name?
Arthur.
Arthur. You are Arthur. Arthur. And you are from Switzerland.
France.
From France. Yeah. Okay. Sorry. But
I think it's the second time you're asking the question.
Yes. Do you remember? But there's another guy here from Switzerland, no?
Probably.
Arthur from France. I remember. What's your name?
Jonathan.
Yeah. Anyway, we have to start. Yeah. Okay, so just to answer the questions, so first of all, Noga said something important that I want you all to hear. So I said at some point that unbiased is consistent, but strictly speaking, it's not true. I mean, it can be unbiased means that the average is the same for all. It's the right theta for all theta, but it doesn't necessarily obviously say that consistent means that not only the average is theta, but the distribution gets very, very narrow at the end and actually centered around becoming a delta function. So the definition of unbiased that doesn't require to concentrate eventually, but this is what's going to happen. So that's why. So in principle, it can be consistent and biased, and it can be unbiased and inconsistent. Many things can happen. All the four cases. But I'm going to tie them together somehow. Now the second question I asked you. Yeah, so it's not strictly speaking, unbiased doesn't lead to consistency, unless I also prove that the variance goes to zero. If the variance goes to zero, then it's going to be consistent. Yeah, and this is really the probability distribution of a certain estimator, like the maximum likelihood or like the maps. So eventually, if I want the variance to go to zero, it should center around something which is reasonable, which is the right thing. Okay, so it's a little more tricky. Now, the second question is I just want you to see that this condition can be tricky So when is the limit and the maximum cannot be exchanged? So for example, think about functions over 0, 1. So I define fn of x as 1 when x is between 0 and 1 over n, and 0 otherwise. So these functions are functions like this. So this is 1 over n, and whatever you want. Okay, so it's 0 all the way here, and then it jumps to 1. Okay? Now, if I'm talking about the open interval between 0 and 1, so let's say that my parameter space is open, and that's actually so it's not compact, as we say. So then if you first take the maximum for every n, this is going to be 1. Okay? Is this clear? So the maximum of fn x over x is 1 for every n. Okay? But when x is strictly inside 0, 1. Okay? Because there's always this little piece up there. But then if I take the limit, if I take the limit n goes to infinity of fn, and then take the maximum, what is it going to be when x is between 0 and 1? So do you see this? And so in the limit, this is going to be pushed all the way to 0, which is outside my space. So in the limit, this one is actually 0. So for every n, this is 1, but in the limit it's 0, which means I cannot replace the limit, change the limit and the maximum in this case. Okay? Do you all see? A little bit mathematical. I mean, a little bit, you have to remember your entry a little bit. So essentially, so I'm talking this particular class of function, which of course is discontinuous. So I can make it continuous. I mean, I can take it, can have something like this. Doesn't matter. So the point is that my space x here is what we call non-compact. It doesn't contain the limit. Okay. So and actually spaceless distributions. For example, think about Gaussian. So the Gaussian distribution is usually not compact space because unless we allow delta functions and zero variances also to be in this space. So a limit of Gaussians with narrowing standard deviation is going to be a delta function. But this is not always considered a distribution at all. So if my space of parameters is compact, then this thing is okay. This particular exchange. But that's why I said that you have to think a little bit about it. But in general, you see here is a very simple example where the maximum before the limit for every n is 1, after the limit is 0. So you can't exchange them.
What is to be compact again?
The parameter space. I mean, essentially, I need the limit of theta, yeah. The set of thetas, if it's not compact, then you can have problems. Anyway, so this is just to make you aware of such details, but it's really not important for us in general. Okay, that's why I put a max and you have to think about it. You have to see that it's actually satisfied when you actually apply. Okay, but that's all right. Okay, so we actually proved that maximum likelihood is consistent. Now I want to show you to talk about the variance again, the variance bias dilemma. And okay, what is it that I want to take away here? So I'm going to show you. So first of all, if you look at the mean square error, the MSE of an estimator, given theta, what is it? So this is so again this is a function of my sample n given theta, and this is what? So this is essentially the expectation with respect to px. So now, okay, px and theta of what? Of theta hat of xn minus theta, the real one, squared. Okay, so there's in general it's a norm, but think about the mobility. I'm writing it in one dimension. Okay, so this is, what is this? So of course I can easily break it into two pieces by adding and subtracting the mean. So this is equal to the expectation, the same expectation of, so I take theta hat, add to it the expectation of theta, the expectation of theta hat, and add it again. This is where this notation is going to be, and minus theta. Okay, squared. This is the same thing, okay? But now I look at this and these two terms separately. You see why? This is going to give me something which depends only on the bias, on the differences in this and the mean, and this is going to depend on the variance eventually. Okay. So you have a plus b square here. Call it this a and this b just to make things. So what is this? So it's a square plus 2ab plus b square. Okay, I must have to remind you this. So so I have two terms here. I have the mean of a square. Okay, again of theta hat minus the expectation of theta hat squared. Again, I omit the.
Could you explain again what is the what's A and what's B?
This is A.
Yeah, but what's special about defining this?
Yeah, so I added and subtract the expectation to this. Now, the reason I do it is because I'm interested in the bias, to separate the bias from the variance. So the expectation of this is going to be the bias squared, and the expectation of this is going to be the variance. So this is a simple trick.
What is the variance?
So I define the variance somewhere here. Yeah, I defined the variance, but maybe I didn't. Here it is. It's the expectation over P of theta hat minus the expectation of theta hat squared. This is how variance is defined. Okay? So this is the variance. And I define the bias here as simply the difference in the mean and theta. So this is going to look like the bias, and this is going to eventually lead to the variance. So that's the whole trick here. Okay, so now, so I have this, which is the variance, or this b theta hat given theta, plus the expectation of the bias squared. So, but this is independent of my sample, because I took already the expectation here. So this is the bias squared, and there's the mixed term, the 2ab. But I claim that the mixed term is 0. Why? Because, because this is the expectation of a product of the expectation by a number. But, so think, so what is the next term? So it's plus 2, the expectation of a p of theta minus the expectation of theta. Theta minus the expectation of theta, theta hat minus the expectation of theta hat, and so on, times what? So it's this term times this term. Okay, so this was the A here, this was my A, And this was my B. No, but here I already took the expectation. This is a number. But this is just the expectation of this minus the expectation of this. The same thing. This is the number. Here the average is already done. Remember, this is the probability of theta hat given x and y. So the only thing which does include theta hat without an expectation would be average. So this is the expectation minus the expectation times a number. So it's 0. So this drops. This is exactly the reason I took the expectation, because the average is going to be the same. So the average of theta hat is the average of theta hat. And therefore I get here E of theta hat minus E of theta hat multiplied by a number, which is 0. Expectation is linear, yeah? So this is the expectation of this plus the expectation of this, but I average already, so this remains the expectation. Everything multiplied by this, and so this is 0. Okay, so what I got here is exactly that the MSE, let me just summarize here, is the variance of theta hat given theta plus the bias square of theta hat. But this is really what we want to minimize if we are using MSE today. So you see that it has these two terms, the variance and bias. Okay, so remember this. And now I'm going to, this is exactly the trade-off. So there is some sort of, this is what we call the bias decomposition of the square error. So the square error is made out of these two terms, the bias square and the variance. So it seems that we actually need to minimize both of them. At this point, we'll follow the traditional statistics. And let's confine ourselves first to unbiased estimators. So for unbiased estimators, I assume that B is 0.
What do you mean when you write MSE of theta given theta, of theta hat given theta? I mean, I don't understand what is this. I mean, variance plus bias square. What is it equal to?
Is this?
What do you mean by writing it this way?
It's just the way it is defined. So this is the mean square error. It was the error, the square error of my estimators minus the true term. What I'm saying, this is actually a sum of two terms. One of them is the bias of the estimator square. The other one is the variance of the estimator. But it's not more than that. Nothing very deep. But now we talk about, so assume that the theta hat is unbiased. Which means that B theta hat given theta is 0 for all sample size. Okay? And then, all sample size, I mean all sample size integer greater than 1 here. Never mind. So, and now I'm actually defining something. So if we already have an unbiased estimator, then the best thing to do is to minimize the variance. Because then the MSE is just the variance. So if this is true, the MSE, the mean square error of theta hat given theta, is the variance. This is obvious, okay? Now, in this case, minimizing the mean square error, which is a good thing to do in general, I want to minimize the spread, is minimizing the variance. And then, so we actually call these things, we call them theta hat is called unbiased theta hat. So unbiased theta hat of xn is called minimum variance. Actually, the other, this is obvious, but it's also called efficient. Efficient estimator if it is minimum variance. It's called efficient if it has a minimum variance among all, with respect to all other estimators. Among all theta hat unbiased estimators. So this is called an efficient. So now I'm going to prove a very important. So actually, there are two parts to what I want to say. First of all, I want to show you that for unbiased estimators, there's a lower bound to the variance. The variance cannot be zero. And this is related to two things which you might have heard of. One of them is coefficient information. Have you heard about it? Maybe or in neural networks. It's a very common object in discussing the stability of neural networks. So this is the first thing I want. And the other one, which is directly related to it, is what we call the Kramer-Rao bound. So essentially, the Kramer-Rao bound is a bound on the variance of an unbiased estimator, and the bound is expressed in terms of what we call the efficient function. So that's what I want to do now.
Can you repeat the last
Sorry?
Can you repeat the last sentence?
The last sentence?
The relation between efficient.
No, so I'm going to relate it. So efficient information is an estimate of stability, which is going to lead to the Kramer bound, which is a bound on the variance of an unbiased estimate. So essentially, I can formulate it as a theorem. Here. So first of all, I defined efficient. Okay. So efficient estimator is an unbiased estimate, is a minimum variance unbiased estimate. Okay. Now, later, the second part of what I will left from this class, or maybe on Monday, is to actually prove that maximum likelihood estimators are efficient in the limit. So they're not only consistent, but they're also minimum variance unbiased. So they're going to be unbiased in the limit because they're consistent.
But you have to compare to something to say that it's minimum variance?
Yeah, among all other unbiased estimates, the minimum achieves the minimum variance with respect to all unbiased estimates. All other. So it's really the minimum among all unbiased estimates. Okay. And then, so then there is a long list of nice properties of distributions. So maximum likelihood is going to be asymptotically efficient. That's essentially what I'm trying to come to. Which means it's going to be not only consistent, as we already showed, but it's going to achieve the minimum variance, which is very good. That's one very good property of maximum likelihood estimators. That's why we love them so much. Because they're also eventually, but I'm actually going to show you even more than that, and we're going to ask, okay, what type of distributions can be efficient for all n, not only asymptotically? This is the next question. This I'm certainly going to do on Monday. This is, and you'll see that these are precisely what we call the exponential families, or the exponential forms. So there's some conspiracy here that all those properties eventually are obeyed nicely in all the nice distributions we all the time use. Okay. So like Gaussians and Poisson and all these things. That's why we use them. But unfortunately, life is not there. Okay. So I'm going to erase this and show you first the Kramer-Rao bound. So this is an important something to remember. So I don't know how much here I can write. We can still see. So there is a theorem. So first of all, let me define. So the efficient information where it's actually going to be a little involved. So I'm defining first of all something which we call the score of the efficient information at a given value theta. By the way, everything that I'm saying today is written in Amir's notes. More or less, maybe I'm saying a few more things, but there are other things that I'm not saying. It's very similar. I just want to make sure that I'm using the same notation. Okay. So I'm defining the score. So we call it fx theta, which is Fisher's score at a given x, and that's why I wasn't sure the notation that I wanted to use is his notation. And this is essentially the logarithmic derivative of px of theta respect to theta. Okay, so we're making all sorts of assumptions here. And the first assumption, of course, is this is a differentiable function. Okay, so this is one thing we implicitly assume. The log of the probability distribution is differentiable, and then essentially at a given value of x, this is what we call the Fisher score. Just a score. It's a very natural thing. It's telling me how sensitive is my probability distribution to the value of theta. So there is some sort of sensitivity. If it is 0, then this is unsensitive. Okay, so this is, I guess, how you saw it maybe in Yoram's course or in some other neural network course, the sensitivity method.
We didn't learn about sensitivity.
You didn't learn about it?
Maybe some other people.
I know that Yoram is running after me, but Yoram.
No, we didn't.
You did. Okay, so let's see it eventually. Yeah, so there are some parallel things. He's going to talk about Fisher, and then he's going to talk about mutual information. I promised him to introduce this before him, but sometimes it doesn't work, so I'm not completely coordinated. Little. So okay, so the first statement or claim or proposition or whatever you want to call it is that the expectation of the Fisher score with respect to x. So the expectation of the Fisher score with respect to x, which is mean with respect to this probability px theta at a given theta of the score, is 0. Okay, why is this true? Okay, it's not obvious. It's not obvious, but it's almost obvious. So the proof is okay. So proof, and I can prove and proof. So essentially, I remember that the probability is normalized. Okay? So this is true for all theta. No, this is also for all theta. For all theta, this is the normalized probability distribution, which means that the integral of the sum of all the x's is 1. Okay? This is all possible x. This is true, by the way, if x is one sample or all the samples, doesn't matter. Okay? So this is normal. This is obviously true. So now I take the derivative of this. So I take the derivative with respect to theta of this integral. So first of all, what do I know about it? The derivative of this respect to theta, the derivative of this respect to theta, which is what? 0. Okay, it must be 0. Now, on the other hand, this is a very common trick. I can, if the boundaries of x don't depend on theta, it's not always the case, by the way, you have to be careful when you do this. So it depends on the parametric family. So if the boundaries of the integral don't depend on theta, then I can take the derivative inside. Essentially, it's like taking the derivative into a sum. So this is just the integral over x of the derivative of p of x theta with respect to theta. Okay, but here comes this simple trick. This is the integral of p of x theta times the derivative of the log. It's actually the ln. So when I said log here, I actually mean ln. Okay? Right. Sometimes I mean log base 2, and sometimes I mean ln. I usually don't use log base 10. This all for engineers and all. So why this is true? Why? Because the derivative of a log is 1 over p times the derivative of p. So the P is going to cancel. So this equals to this. This is the trick that we use all the time. Remember. Because the derivative of ln is 1 over times the internal derivative, which is dp. So the 1 over p is going to kill the p. Okay? Okay, but that's precisely what I call the expectation of s. This is just e with respect to ps of x of t of d log p x theta respect to theta. This is what it is, yeah. This is the expectation of this. Okay, so this is 0. Okay. So this is what we call QED here. That's what we always like to say here. We showed what we wanted. Okay? Is it clear? This is tricky, but it's really very simple. Okay, so essentially this is the expectation of this is 0 because the probability distribution normalized. Okay. So now
Is there some intuition why it's true? I mean, the derivative of log is
what is true? Why this is true?
Yeah.
I just proved it.
No,
yeah.
true, but maybe
it's not intuitive.
Yeah.
Yeah. Okay. You don't have any intuition about this quantity at this point. You'll develop it later on.
But you have to do it.
You'll get it. You'll get it through the proof. I mean, this is one of those things that comes out of the blue. Don't know whose is this, but I don't want to know the flow. I'm moving too much. So essentially, and so I guess this is some sort of a lemma. I'm just trying to develop some sort of feeling. How is this quantity, the score behaves? So at this point, you don't have any intuition about it. It's just some, out of the blue. I define the logarithmic derivative of the distribution. But now I'm going to So now I'm going to assume. I need more boards because I can't write there because I don't see anything. Yeah? Okay, so I'm going to assume that I'm going to use the unbiasedness in a very simple way. So what else do I know about my estimate? So this was so I defined this score. This score is a property of the family. It has nothing to do with the estimate. I mean, this is a number that depends on x and theta. For every x and theta, it's this number. Its average is 0. That's one thing I showed before. Now I'm going to take my estimator. So I know that if it's unbiased, unbiased means that the expectation with respect to px, n, and theta of theta hat is what? Is theta hat. I'm sorry, is theta. I'm sorry. That's not what I want to write. I know that theta equals the expectation of px and of theta hat. So this is unbiased. Unbiasedness. Okay, this is what it is. Okay? Okay? Now, but let's write this explicitly. So this is the integral. Allow me to call it x just to make it simple. So again, the integral over x of px given theta times theta hat dx. Okay? So this is equal to theta. But now I do the same trick again. I take the derivative with respect to theta of both sides. Okay? So I take this and take the derivative with respect to theta of this equation. So what is it? Derivative of d theta of theta. What is it? Altogether? 1. Okay. 1. And the derivative, now, okay, so 1 equals the derivative of this with respect to theta. I'm going to do exactly the same trick. I'm going to get it into the integral, and then take this is independent of theta. So I only have to take this But then I'm going to write it in the same way exactly. So this is the integral of px given theta of the logarithmic derivative of px theta respect to theta times theta hat. Okay? I did this trick already here, so it should be familiar by now. Okay? Same thing. Okay, but what is this? So this is an expectation of a product. X is the random variable over which I'm averaging, and this is like A of X and B of X. Okay? So what do you know about the expectation of a product? If the product expectation is uncorrelated, if they're independent, they're also uncorrelated, but they can be uncorrelated, not independent. So in general, we say that they are uncorrelated. And otherwise, so what do I know? So essentially, if you have two variables, in general, let's call them x and y, what do we know? So we know that the square of this is less than equal the variance of x times the variance of y. Actually, it's always ruled like this. The expectation of x squared times the expectation of y. Now, this is known in the literature as the Cauchy-Schwarz inequality, or the generalized Cauchy-Schwarz inequality. So this is something I have to explain. Where it's coming from. This is, the easiest way to remember this. Think about dot product of two vectors. So the dot product, if I have two vectors, so A times B, what is it? So it's the absolute value of A times the absolute value of B times what?
Cosine.
The cosine of the angle between them, whatever it is. And cosine, so essentially the cosine of an angle, absolute value, square is always less than 1. Okay? Okay, so this means that A dot B square, or absolute value square, divided by A square B square is less than 1. So that's the simplest way of seeing the Cauchy-Schwarz inequality. And now we can just extend it to vectors in Hilbert spaces, or to random variables, or to many other things. Okay, so this is simply called the Cauchy-Schwarz. Don't ask me to spell Cauchy, but it's probably Cauchy. A-U-C-H-Y. Okay, Cauchy-Schwarz. Cauchy-Schwarz inequality. Okay. So if this is true in general, so this is just, if you don't believe me, read it in Wikipedia, I don't know where. So this is also true, that x minus the expectation of x multiplied by y minus the expectation of y is less or equal the variance of x times the variance. So it's a special case of this, because that subtracted the mean. Okay, so this is what I'm going to use here. So here I have, so this is Cauchy-Schwarz inequality in general. Always true. I mean, no, square, I'm sorry. This has to be squared. It's less than this. Just like here, square of the magnitude. So, and the variance is already squared, so it's alright. So I'm going to bound this by what? So this is an expectation of a product. So I know that the square of it is going to be smaller than the product of the variances of these two things. Okay, so now allow me to erase everything here. I'm just using the Cauchy-Schwarz inequality. So this is less than, so actually I know that even the absolute value square of it, which is also 1, because 1 square is 1. So this is 1, is less than the variance of A, which is this, times the variance of theta A. but that's what I really wanted. So it's less than the variance of the this Fisher score variance with respect to x, times the variance of theta hat. So this is simply Cauchy-Schwarz inequality. Okay, so this is nice, because what we got is that the product of these two variances is greater than 1, greater or equal to 1. Or in other words, so all this was just scaffolding to actually get me here. So essentially, I got that the variance of the estimator, conditioned on theta, which is what I'm interested in, is greater than 1 over the expectation, the variance of the Fisher score. Okay. So what is this variance of the Fisher score? This is essentially almost what we call the Fisher information. What can I erase now? Really, such a small board. So, okay, so let's push this here. No, I had to fight to get this board doubled. I had to make it triple. Okay, so now we're talking about the variance of this estimator. Remember, it's the width of this distribution which we just erased. So let's just express this variance of the Fisher score more carefully. 2 minutes. So the variance of the Fisher score, since the Fisher score has a 0 mean, so the variance is just so this variance of d log of the Fisher score, d log px theta to d theta, is essentially the expectation with respect to x of the square of it. In just a second moment, because the mean is 0. Okay, that's why I proved that the mean is 0. So subtracting the mean doesn't change anything. Okay? And so for a single x, this is what we call the Fisher information, J of t. This is just a notation. This is the definition of the Fisher information. Now notice that if this is for a single x, one sample. Now if I actually had a big sample here, an n times, so if it's the Fisher information of a sample, now this average square. So first square and then average. Okay, sometimes I prefer to use this notation. It's easier. So now it's with respect to all the samples. But if it's an IID sample, that's why the log p is so useful. If it's an IID sample, this is simply a sum. So it's a sum of exactly the same term because I'm averaging of all these. So this is simply n times j set.